Hello everyone and welcome back to our Automata and Formal Languages class and into our Unit 5. What I'm going to do in this unit is I'm going to go over the proof of the union regular expression that we did in Unit 4, so we get another good sense of what is going on in this class when we do our proofs for certain theorems by construction. But if you have finished your Unit 4 and you feel comfortable about the proof that we did for the theorem that the class of regular languages is closed under the union regular expression, then you should be good. You can skip this part 1 of Unit 5 and proceed to part 2, in which we will see an example of the closure of union and how you can actually build a finite automaton, deterministic finite automaton, based on two smaller deterministic finite automaton, such that the bigger finite automaton accepts the union of the two languages, or recognizes the union of the two languages. So first off, the first thing that I'm going to do here is we're going to go over the terminologies we started and we discussed last unit. The idea of formal computation. When we talk about computation and formally define it, we will say that computation is basically acceptance of a sequence of states. So in our case, in the case of strings and finite automaton, we would say that let M be our finite automaton. And if you remember, the finite automaton is a 5-tuple. It's composed of Q, a set of states, sigma, a set of its alphabet symbols, delta, its transition function, Q0, its start state, and a set F, which is a finite set of accept states. And then we say that let W be a string in which W sub I, for all of these numbers, to come from W sub 1, W sub 2 to W sub n, come from the alphabet set, the set of alphabet symbols. Then we say that M accepts W. So in any kind of sense, if W is a sequence of operations, a sequence of computations, we will say M computes. So we say M accepts W if there exists a sequence of states from Q such that the three following conditions meet. What that means is that so these three conditions that we want be met is if R sub 0, or the first state in the sequence, is the Q sub 0, the start state of our automaton, R sub n, the last state in this sequence, to belong to F, or be one of the accept states of my finite automaton, and then for every R sub I and W sub I plus 1, so for every state, if the next symbol of my alphabet takes me to the next state in the sequence. So basically, what that means is that whenever we are in some R sub I, let's say we are in this state, and then we see the next symbol, these two together from the transition table take me to R sub 2, and that for every other R. If these three conditions are met, we will say that our finite automaton accepts this string. We then, from this point on, are going to talk about regular operations. Basically, they are kind of like multiplications and addition in terms of arithmetic and numbers. These are for strings. And we define these three operations as being regular operations, and we show that if you have an automaton that accepts the languages, if you combine these two languages with these regular operations, then the combination of these languages are regular. And we'll get to this next. Okay, so the three basic regular expressions that we will be talking about when we combine languages are union of two languages, concatenation of two languages, and the star of a language. Now, when I'm going to talk about the union as a kind of a byproduct of that, I will also talk about the intersection of the two languages, as well as the complement of our language. So in this unit, we will cover these three operations: union, intersection, and complement, because they're fairly similar to each other. And we will show that we can use our toolbox of non-deterministic finite automaton that we defined as a machine that accepts a regular language, and by that definition, now we have the definition of regular language. We say that a regular language is a language is regular if a finite automaton accepts it. Now, if we can show that, we can build finite automatons off of other languages that we know are regular. Then the big finite automaton accepts that the combination of these languages through union, intersection, and complement. And as a result of that, we show that these three operations are closed for the class of regular languages. And from this point on, I want you to think about a language as being a set. So when I say a language, by definition, it means that it's a set. Okay. So what is the union of two sets? If you have set A and B, union by definition, actually I probably should put like a little delta on top of these because these are definitions. So by definition, union of two languages is composed of all members of both languages. So it's a set of X such that X belongs to A or X belongs to B. Remember that this OR is an inclusive OR, which means that if X belongs to both A and B, it's still in the union. As a result of this, we also define the intersection of two languages A and B to be the set of all members such that X belongs to both of them. So as X belongs to A and X belongs to B. And the complement of a language is by definition the member of all X such that X is not in A. And remember, when we talk about this, we talk about X in light of a universal set. And so the universal set is a set that's composed of our alphabet symbols. That's what we consider being members of a language to be drawn from, or strings from a language to be drawn from. And so then the next operation that we will be talking about is concatenation. And I'm going to show you by the end of this unit that we will run into problems trying to prove that the class of regular languages is closed under concatenation with the toolbox we have now. And so then I will show you that now that this toolbox is limited, we have to rely on building another toolbox, and that's what we call a non-deterministic finite automata. And then we can show that the class of regular languages, or prove that the class of regular languages is closed under concatenations, and same with the star operation. So what does concatenation do? Concatenation of two languages is a set of strings in such a way that if you break this string into two parts, the first part to come from the first set or the first language, and the second part to come from the second language. So that's what the concatenation here does. So and I'll give you an example. And star is is a set of all the strings. If you combine them in any kind of format from the language, then or ordering. The star is basically a sort of a universal set built on top of a set. So an example that I showed you in the last unit is basically I said let's have two sets. Let A be the set of good and bad, two strings, and B be the set of boy and girl. Then the union of A and B is good, bad, boy, girl. And then I remember, because these are sets, the union and any of these combinations don't really need for these set members to be in any certain order. So it could be good, bad, boy, girl, or it could be boy, girl, good, bad, or it could be boy, bad, good, girl, and however permutations of these 4 elements you want. Concatenation, though, is basically a set of all the strings such that the first, they're made of 2 strings put together from each of the 2 sets, and then such that the first string is from the first set and the second string is from the second set. So if I say concatenation of A and B is the set of good boy, so the first string coming from A, the second string coming from B, so it could be good boy, good girl, and then bad boy, bad girl, right? But it couldn't be boy good or girl good, girl bad. That would be the concatenation of B and A. So basically, if I say B concatenated with A, then it would be boy good, boy bad, girl good, and girl bad. Okay, so that would be the concatenation of B and A. Star is a set. Star of a set is a set of all strings from the original string put together, or concatenated together. So, for example, star of A will be if no strings from A are concatenated together, so that would be epsilon or the empty string, and then one string from A, so it would be good or bad, then string A repeated, so it could be good, good, and then string A concatenated with string bad, so good, bad, and then string bad concatenated with good, bad with bad, so you do like 2 permutations of these, and then 3 permutations of these, and then 4 permutations of these. So it's going to be an infinite set of all the strings that are drawn from set A in any kind of ordering, and that is the star operation. Now, our plan here is to show that if A and B are regular languages, then their union is going to be a regular language. As a result of that, we'll show that their intersection is also a regular language, as well as the complement of each of these regular languages is going to be a regular language. Then we want to show that the concatenations of 2 regular languages are regular, as well as the star of regular languages are regular. Alright, so I'm going to now go again ahead and talk about the proof of the theorem that we covered towards the end of the last unit, and that is that the class of regular languages is closed under the union operation. It's a very, very important theorem for us, because what it would allow us to do is to build complicated languages based on smaller languages that can be thought of as being union of smaller languages, or rather simpler languages. And since the simpler languages may be, if the simpler languages are regular, then we effectively have created a regular language. So this theorem is a very, very important theorem for us. In other words, mathematically speaking, if A sub 1 and A sub 2 are 2 regular languages, then the language that is created by unioning these 2 languages is also regular. Remember, we talked about earlier in the last unit that we defined what a regular language is. We said that a regular language is a language such that all strings generated with it, or all strings that are in it, can be or are accepted by some finite automaton. So effectively, the idea is for us to represent each of these languages with their finite automaton. So let's say that if you have a finite automaton M sub 1, and if its language is A sub 1, meaning that M sub 1 accepts all strings from A sub 1. And same thing with M sub 2, if we have a finite automaton, finite deterministic automaton M sub 2, such that all strings that are generated and are within A sub 2 are accepted by it, then we want to build an automaton based on M sub 1 and M sub 2 that accepts the languages. If we can build a finite automaton based off of the 2 M sub 1 and M sub 2 such that it accepts strings from A sub 1 or A sub 2, then we have proved this theorem. And proof in this theorem is proof by construction. So, as I said, we want to prove this theorem by construction, and I'm going to now go ahead and redo this proof quickly for you. so that you will see how the proof of construction for this particular case is done. So again, the idea here is that I assume that I have a finite automaton M sub 1 that recognizes language A sub 1 and a finite automaton M sub 2 that recognizes the language N sub A sub 2. So let's suppose that M sub 1 is a finite automaton, so it's going to be a automaton that is a 5 tuple, so I have a Q sub 1, a sigma, a delta sub 1, a Q sub 1 0, and an F sub 1, such that Q sub 1 is my set of states, so it's going to be Q sub 1 I, such that, let's say that I is natural number and I is between 0 and N. Sigma is my language, or alphabet rather. Q sub 1 sub 0, Q sub 1 0 is my start state, so it's the start of M sub 1, and F sub 1 is this accept state of M sub 1, so it's going to be Q sub sub 1 J, such that Q sub 1 J accepts strings of W from A sub 1. Okay, so so that's my first automaton, and then automaton M sub 2 is another 5 tuple, Q sub 2, sigma, delta sub 2, Q sub 2 0, and F sub 2. And basically again, Q sub 2 is a set of Q sub 2 comma I, such that I is between 0 and, let's say, M this time. Sigma is my alphabet. And Q sub 2 sub 0 is my start state of M sub 2, and F sub 2 is the set of all Q sub 2 J's that Q sub 2J accepts W from A sub 2. Okay. Now this is my important formalization of the two finite automaton. I didn't do anything really crazy so far. All I did is that I basically formulated these two things. There's one thing that I haven't talked about yet, and those are the transition tables. So delta of so delta is my transition table that takes a state, let's say Q sub 1 and K, and a symbol A from the alphabet, and it goes to Q sub 1 K plus 1. Okay, so basically this transition table says that how my Q sub 1 moves through when every alphabet symbol is encountered. Same thing with, so this is delta sub 1. And delta sub 2 does the same thing, but for Q2s. So if you are in state Q sub 2K, and then you say a symbol, then you go to Q sub 2 and K plus 1. Let me make this a little bit neater and cleaner for you. So this one's going to go to Q sub 1 and K plus 1. Actually, let me rewrite this. So the delta 1 of Q sub 1, let's call this H, and A goes to Q sub 1 and H plus 1. Perfect. So how am I gonna now go ahead? How am I gonna go and do the bigger language? So look at what this language, what each of these finite automata that I have are. Each of the finite automata is 5 tuples. So when I combine them together, I want to create a 5 tuple M that is equal to Q sigma delta Q sub 0 and F. If I build this automaton M that accepts the languages in A sub 1 or A sub 2, then I have proved my theorem that there is an automaton that accepts strings from the union of language A sub 1 and A sub 2, and by definition then the union of A sub 1 and A sub 2 must be regular, because a regular language is defined as a language such that a finite automaton accepts all its strings. So how can I build this automaton? To do that, I know a couple of things are kind of trivial. The first thing that's kind of trivial is is if the alphabet between the two languages are the same, then sigma for the union of them is the same. So in this case, I suppose that alphabet for the two languages are the same, so I use the same alphabet for this language, and that's by default built. So the second part of my 5 tuple is defined. Now if the two languages had different alphabets, then all I needed to use is their union of their alphabets as the alphabet here, and I would be good. Next, I would like to show that there is a set of states that I can design, and a transition function for that new set of states, a start state and a final state or an accept state for this automaton that basically performs the computation of these two automata at the same time, M sub 1 and M sub 2. How am I going to do that? So let me just draw a picture for you here, and then let's see if you can see how it's done. So if you look at the M sub 1, let's say that M sub 1 is an automaton, basically just like what we have seen so far, that it has a start state, okay, and we know that this start state is Q sub 1 0, and then there is a transition mechanism for this that goes between a bunch of states, and then it reaches an accept state or a set of accept states, right? So if we can kind of set this up, and let's say that this is our M sub 1, right? Okay, and then we have another machine, M sub 2, with its own start state, and this start state is going to be Q sub 2 0, and that it goes through a bunch of transitions, and then it reaches some accept states. Okay, so my idea is to build these two together so that when I go through a symbol, and let's say that you have a string of, let's say, A sub 1, A sub 2, all the way to A sub W, and that if you start and go through these sequences of symbols, these machines will go through their transitions, and then they end up in some state. Now, if that state is an accept state, you accept that language, they accept that language. If it's not an accept state, then they do not accept the string. So what I want to do is that I want to show that there is an automaton built on top of these two that simulates them side by side together, so that when you go through each of the symbols, then you end up in some final state, some state, and that if either one of these two languages, two automaton accepts, then my combination accepts. If not, then my combination does not accept. Now, the first thing I need to do, let's actually do it backwards. Let's start with the final state, right? So the final state should be in a form that will have either one or both of my original m sub 1 and m sub 2 accept states. If that's the case, then my automaton will accept. So it's really easy to see that the final state would be a set of some things that would contain within those things accept states of either one of the two languages. So we know that. Same with the start state and same with the set of states. So how can we simulate these two automaton together? Here's how I'm going to do. I'm going to build Q to be Q sub 1 cross Q sub 2. When that happens, then you see, then this Q is going to be a ordered pair of Q sub 1 I comma Q sub 2 J, such that Q sub 1 I is from Q sub 1 and Q sub 2 J is from Q sub 2. Right? Now if I build my Q this way, then in every state of M, it's a tuple, it's a binary pair that has one state from the M sub 1 and one state from the M sub 2. Therefore, if I build my transition function over these states, then that transition function is going to basically have inside of itself a transition for M sub 1 and transition for M sub 2 side by side. So when I see one item, one symbol from my string, then I can simulate both these machines together. In other words, let's say that if my machine encounters A sub 1, it makes a copy of A sub 1 and passes it to M sub 1, and it makes a copy of A sub 1 and passes it to Q sub 2 or to M sub 2 to process together. So that's what happens here. Now let's look at the transition function. How does my transition function look like to be able to compute the two transitions of my original automaton? It's fairly straightforward to see how it can be done. If my delta, and as a result we know that delta is going to be from Q over sigma to Q. So as a result of this, basically the delta is from Q sub 1 cross Q sub 2 cross sigma to Q sub 1 cross Q sub 2. What that means is that each of these is going to be a binary pair or ordered pair, an alphabet, and then the result is going to be an ordered pair. So how will I define it? I'll say that the delta of Q sub 1 I comma Q sub 2 I, or let's make this J. Okay, so the delta of cross product of these guys and A from my alphabet, okay, is going to be equal to a pair, binary pair or ordered pair. And what is each of these is going to be? Each of these is going to be the transition of each one of my original transition tables. So this is going to be delta sub 1 of Q1I and A, comma, delta sub 2 of Q2J and A. And see, I have from my transition tables for each of these guys, I already have the transition table of my my combination. This ensures that, and I'm going to write this. This ensures that each input symbol is going to be processed by both M sub 1 and M sub 2. Which means that my machine having this transition table and this set of states, my machine M will simulate machine M sub 1 and machine M sub 2 side by side. So the computation that machine M goes through over the sequences of symbols is essentially the same computation that machine M sub 1 goes through the symbols and machine M sub 2 goes through the same set of symbols or sequence of symbols. So that ensures that that's the case. Which one should be the start of my machine M? It's easy. The start of my machine M is the start state of machine M sub 1 and the start state of machine M sub 2. So that ensures that when the first symbol is read, it's processed by both the start state of machine M sub 1 and the start state of automaton M sub 2. So that kickstarts both of M sub 1 and M sub 2 to keep my process intact. How about F? What should be my accept state of machine M? The accept state of machine M is a set of binaries Q1 sub I, Q sub 1 R, and Q sub 2 R, such that Q sub 1, actually let's call this R prime, R is from the accept state of F sub 1, and Q sub 2 R prime is from the accept of F2. What this means is that the set of accept states of M is a set of ordered pairs in which let me clean this up. It's a set of ordered pairs in which at least one of the pairs members is an accept state. What this means is that when I give copies of A sub 1 and A sub 1, A sub 2, A sub 3, all the way to A sub W, copies of the input symbols, and feed them into my machine M sub 1 and machine M sub 2, and I end up at some final state here and then some final state here, my machine will accept, my combination machine, my union machine will accept if either one of these two is an accept state. Remember, see, I said at least one is an accept state, which means that F is going to be from Q sub 1 cross F sub 2 union of Q sub 2 cross, or rather F sub 1, or F sub 1 cross Q sub 2. See, because I want the state to have at least one accept state. Okay, so if the first state is any state from the first machine, but the second state is an accept state from the second machine, or in this cross product here, if the first state, the Q sub 1I, is an accept state, and the second state is any state, then my machine accepts. So if either one of the states in my pair, in my ordered pair, is an accept state, then my machine accepts. So this covers all the 5 aspects. So I created the Q to be the cross product of the states. I created the delta to be this transition table. I created the Q sub 0 to be the pair of the start state of first machine and the start state of the second machine, and I created the final accept states to be sets of pairs of states from the first and second machine, such that either one of these states is an accept state in their own respective machine. Then I have my finite automaton that accepts any string that comes from the union of a sub 1 and a sub 2. Therefore, union of a sub 1 and a sub 2 is regular. So basically what this means is that Q ensures M processes symbols by simulating M sub 1 and M sub 2 simultaneously. Delta ensures that each symbol is properly processed by M sub 1 and M sub 2. So this is number 1, this is number 3. And number 2 is the sigma, so I know that the sigma is already done. Sigma is here, sigma is here. Number 4 ensures that M is the start, or M starts at the, so M starts at the start of both M sub 1 and M sub 2. And 5 ensures that if M sub 1 accepts or M sub 2 accepts, then M accepts. And we are good. We have covered or built a machine, finite automaton M, with designing its Q, its sigma, its delta, its Q sub 0, and its F, based on M sub 1 and M sub 2, that accepts any language that either M sub 1 accepts or M sub 2 accepts. Rather, accepts any string that either M sub 1 accepts or M sub 2 accepts. As a byproduct of that, M is recognizing the union of A sub 1 and A sub 2. Therefore, by definition, the union of A sub 1 and A sub 2 is regular.